Okay, in this section, we're going to talk about section 9.2, dealing with multi-stage experiments. And in this section, we're going to find probabilities involving multi-stage experiments. Also, we'll find probabilities involving independent events and find conditional probabilities. All right, so let's start with multi-stage experiments. Okay, so here we're going to consider multi-stage experiments, which are what we call compound events. And they are completed in multiple steps, like if we were flipping a coin twice or rolling a die twice. Now, multi-stage experiments can be done either with replacement or without replacement. Now, I'll talk more about those two, with replacement and without replacement. All right, in this case, so let's look at a multi-stage experiment with replacement. Multi-stage experiment with replacement. Let's say we consider a ball being drawn from the box and its color is recorded. Then the ball is replaced, a second ball is drawn, and its color is recorded. A tree diagram, as you see here, for this two-stage experiment is provided. And the tree diagram can be used to generate the sample space. Each of the outcomes of the sample space are equally likely, and there are 9 total outcomes. So the probability of the event containing each separate outcome is 1/9. And as you can see, here's the tree diagram. So on the first draw, a red ball or a white ball or I'll say gray ball is drawn. One of those three can be drawn. So its probability for each one will be 1/3 because there are 3 balls in the box and each ball is of a different color, red, white, and gray. Then on the second draw here, the first ball was recorded and then it's put back in the box. So now on the second draw, it's still going to be a probability of 1/3 because on the second draw, you still have 3 possible balls to draw, a red, a white, or a gray. Okay, as you can see for each one of these branches here. So now these are all the possible outcomes, as you can see here, and each outcome has a probability of 1/9. So this is an example of a tree diagram where a ball is drawn with replacement. Okay, now let's look at this first example that deals with replacement. A box contains 4 white balls and 3 black balls. Suppose that a ball is drawn at random from a box. Its color is recorded and then the ball is put back in the box. So now we're dealing with something with replacement. Then a second ball is drawn at random from the box. Draw a tree diagram from this experiment and find the probability of every event that the 2 balls are of the same color. I mean, the probability of the event that the 2 balls are of the same color. So let's look at what we have here. We have 4 white balls. So here, this is just a representation of 4 white balls. So these are 4 white balls, and then we got 3 black balls. So I'm just shading in 3 black balls here. Okay. And we want to say that the ball is drawn at random from the box. So we're going to draw twice. On the second draw, it'll be drawn with replacement. So here's how we do the tree diagram. On the first draw, it could be a white ball or a black ball. And I'm letting W be white and B be black. Then I'm going to record the probabilities along the branches here. So the probability of drawing a white ball, there are 4 white balls out of a total of 7. So this will be 4 sevens. And for a black ball, there are 3 black balls out of 7. So that probability of drawing a black ball would be 3 sevens. Now, the color's recorded, and then put the ball back in the box for the second draw. So this is with replacement. So on the second draw, we can draw either, if the first ball was white, we can draw either another white ball or a black ball. Or if that first draw was a black ball, on the second draw, it could be a white ball or another black ball. So that means that the probability will remain the same since it's being done with replacement. So the probability of drawing a white ball on the second draw would still be 4 sevens, and it'll still be 3 sevens for drawing a black ball on the second draw. Now, if the first draw was black, the probability of drawing a white ball will be 4 sevens, and the probability for drawing a black ball on the second draw will still be 3 sevens, since all of this is done with replacement. Okay, so now I'll write down the outcome and, of course, the probability. All right, the outcome will be a white ball and then a white ball. So here I'm listing all the outcomes here from this tree diagram. Then another possible outcome would be a white ball and then a black ball. The third outcome would be a black and then a white ball. And then the final would be a black and a black. Excuse me. Now, to find their probabilities, we just multiply along the branches here. For a white and a white, it'll be 4 sevens times 4 sevens, which will be 16 over 49. And then for a white and a black, this will be white and then black, 4 sevens times 3 sevens, which will be 12 over 49. And then for a black and a white, that's 3 sevens times the 4 sevens. That's going to be 12 over 49 as well. And then finally, a black and a black, 3 sevens times 3 sevens. That will be 9 over 49. Okay. So this is the tree diagram for this experiment. And now we want the probability of the event that the 2 balls are of the same color. That means I need the probability that I'm going to get either 2 white balls, which is this outcome, or 2 black balls, which is this outcome right here. So the probability of getting a white or a white, a white and a white, or a black and a black. That means the 2 balls are the same color. Well, let's look at the probability of getting a white ball, getting 2 white balls, and then we're going to add that to the probability of getting 2 black balls. And in this case, the probability of getting 2 white balls is this 16 over 49. Now I'm going to add to it the probability of getting 2 black balls. That's 9 over 49. So 16 49s plus 9 over 49 would be 25 over 49. So the probability of the event that the 2 balls are of the same color would be 25 over 49. Okay. All right, now let's talk about some things that are related to this tree diagram that I created. All right, in this case, the sum of the probabilities on all the branches from any point will always equal 1. Okay. So these branches here, the sum of those probabilities will be 1. And on these two branches here, the sum of the probabilities is equal to 1, and the same thing here. The probability along those branches from any point is going to be equal to 1. Also, the sum of the probabilities for all the possible outcomes must be equal to 1. So if you take the time to add up each individual probability that you see here on the far right, they must total 1. So here is a general theorem for this, the multiplication rule for probabilities of tree diagrams. For all multistage experiments, the probability of the outcome along any path of a tree diagram is equal to the product of all the probabilities along the path. Okay. All right, now let's look at independent events. Independent events. And that's this. When the outcome of one event has no influence on the outcome of the second event, we have what they call independent events. For example, if two coins are flipped and event E1 is obtaining a head on the first coin and E2 is obtaining a tail on the second coin, then E1 and E2 are independent events because one event has no influence on possible outcomes. So now let's look at example 2. We're assuming the probability is 1/2 that a child born at any time is a girl and births are independent. So the outcome of one birth has no influence on the birth of the previous child. What is the probability of the event that if a family has 5 children, where you have no twins, they are all girls? Okay, so the probability of a girl dealing with a single birth, that's going to be 1/2. That's given to us. But now we want the probability that a family has 5 children and they're all girls. And we're assuming that those votes are independent, so one has no influence on the other votes of the other child. So this will be 1/2. Then we have to multiply by the probability of getting a second child that's a girl is 1/2 times the probability that the third child is a girl, that's still 1/2 times another 1/2 times 1/2. So here we're using 1/2 as a factor 5 times. So if I multiply the ones on top, it'll be 1. 2 times 2 times 2 times 2 times 2 would be 32. So if a family has 5 children, the probability that they are all girls will be 1 out of 32. Okay. All right, now example 3. Each question of a 5-question multiple choice exam has 5 possible answers. Suppose a student picks an answer at random for each question. Find the probability the student selects the correct answer on all the questions. So here we're going to find the probability of a correct answer on just a single question. Now, it's a 5-question multiple choice exam. And each question has 5 possible answers. So that means there is a 1 out of 5 chance that the answer that that student selected is correct. So that probability will be 1/5. So for a 5-question multiple choice question where all 5 answers are correct, the probability of selecting 5 correct answers on a 5-question multiple choice question, we take 1/5 and multiply that as a factor 5 times. And we're assuming that the answers that they give are independent, or the answers that they choose are independent. So multiply numerator times numerator and denominator times denominator. I have a 1, and then if I do 5 times 5 times 5 times 5 times 5, or 5 to the 5th, I'm going to get 3,125 in the denominator. So the probability that the student selects the correct answer on all 5 questions will be 1 out of 325. Okay. All right, next we'll look at without replacement, a multi-stage experiment that's done without replacement. And that's this. When the occurrence or non-occurrence of an event A has an influence on the occurrence or non-occurrence of event B, the events A and B are independent. All right, so let's say in this example that we have 2 balls that are drawn one by one without replacement. So here I got a black ball and 2 white balls in the box. And if I want to draw a tree diagram of every outcome and their corresponding probabilities, this is it. So on the first draw, I have a black ball and a white ball. The probability of drawing a white ball is, of course, 1 out of 3. I only have 1 black ball out of 3. And the probability of drawing a white ball will be 2/3. But now, let's say on the second draw, if the first ball that I draw is a black ball, on the second draw, I'm only going to have two balls left. So this is without replacement. That black ball will not go back in the box. So I have 2 white balls left. So the probability of drawing another black ball will be 0 out of 2. But the probability of drawing a white ball, that will be 2 out of 2, which is, of course, 1 whole. That's a certain event. 0 over 2 is 0. That's an impossible event. Because if I've drawn the only black ball out of the box, I'm not going to be able to draw another black ball on the second draw. So that's an impossible event. Now, let's say that on the first draw, I draw a white ball. That would mean, if I cover one of these white balls up, I'm only going to have a black and a white ball. A black ball and a white ball. So the probability of drawing a black ball will be 1/2, and the probability of drawing another white ball will be 1/2. Okay. So without replacing means I'm going to have fewer balls in the box, and the probabilities will change on the second draw. Excuse me. And these are all the outcomes here along the branches of that tree. And for me to draw 2 black balls, that probability will be 1/3 times 0 over 2, which is 0. For a black and a white, that probability will be 1/3 times 2 over 2, which will be 1/3. And then the probability of a white and a black, 2/3 times 1/2 will be 1/3. And then finally, drawing 2 white balls, that probability will be 2/3 times 1/2, which will reduce to 1/3. Okay. And you'll see along these branches here, the sum of those probabilities along each of these branches in this tree diagram has to add up to 1. And for all the possible outcomes, the sum of the probabilities for those possible outcomes will have to be equal to 1. Now, take a look at this example here where we're going to draw a tree diagram of this. In this case, I need to move this paper up a bit so you're not confused. Here we go. Says your box contains 4 white balls and 3 black balls. A ball is drawn at random from the box and not replaced. Then a second ball is drawn at random from the box. Draw a tree diagram for this experiment and find the probability of the event that the 2 balls are of the same color. So I'll go ahead and draw in the 4 white balls and 3 black balls. So on the first draw, I'm either gonna pull out a white ball or a black ball. So the probability of drawing a white ball, there will be 4 white balls out of 7. So that's 4 sevenths. And then the probability of drawing a black ball will be 3 out of 7. And now on the second draw, now assuming that we're told that the ball that was drawn on the first pick will not be replaced. So that means our probability will be changing when we find out what that probability is for drawing either a white ball or black ball on the second draw. If the first ball was a white ball, that means I'm going to be down to only 3 white balls because it's not going to be put back in the box. But this time, the total number of balls I have left will be 6, okay? So the number of balls has reduced to 6, but I have 3 white balls to choose from. That probability now becomes 3 over 6. And the probability of drawing a black ball, given that I'm drawing a white ball out of that box, now is also going to be 3 over 6. And that 3 over 6, I can go ahead and reduce that to 1/2. Now, let's say on the first draw, we drew a black ball out of the box. So on the second draw, it could be white or black, but I know that I've drawn a black ball out of the box. Well, if I've drawn a black ball out of the box this time, my sample size has dropped from 7 to 6. And how many white balls do I have left to draw from? This time is 4. So that probability of drawing a white ball, given that a black ball was drawn out of the box on the first draw, would be 4 over 6, which reduces to 2/3. And since a black ball was drawn out of the box, I have only 2 left out of 6. So the probability of drawing a black ball, given that a black ball was drawn first, would be 2/6 or 1/3. Okay, so now I'm gonna list all the outcomes and their respective probabilities. So I now have a white and a white, then a white and a black and a white, and then a black and a black. So the probability of drawing a white and a white multiply along the branches here. 4 sevenths times 1/2. This will be 4 over 14, but I can reduce that to 2 sevenths. And then for a white and a black, there's a white and a black, 4 sevenths times 1/2. Which is also going to be 4 over 14, which is 2/7. And then for a black and a white, that'd be 3/7 times 2/3. This will end up being 6/21, but I can reduce 6/21 to 2/7. And then finally, a black and a black, 3/7 times 1/3. Which will be 3/21, but I can reduce that to 1/7. So if I add along all those probabilities for each of those outcomes, they add up to 1. And if I add the probabilities along each of these individual branches, they add up to 1 as well. Now we want the probability of the event that the two balls are the same color. In other words, the probability of 2 white balls or 2 black balls. And in this case, the probability of a white and a white or a black and a black, we just add the two probabilities together. The probability of 2 white balls and the probability of 2 black balls. So the probability of 2 white balls here came out to be 2/7, plus the probability of 2 black balls, that came out to be 1/7. Add 2/7 and 1/7 together, you'll get 3/7. So the probability that 2 balls of the same color would be 3/7. Okay. All right. Here's another example of an independent, well, something with replacement and without replacement. All right. A box contains 7 letters shown as charted, CHARTED. What is the probability of the outcome read, RED, in that order if 3 letters are drawn one by one with replacement and without replacement? All right, so in part A, we want the probability of getting RED in the order where the 3 letters are drawn one by one with replacement and without replacement. So I just need the probability of drawing an R first, and then an E, and then a D. And these are done with replacement. So the probability of drawing an R, there's only one R in the word charted. And in this word, there are 7 letters in the word charted. So the probability will be 1/7. And that letter will be put back in the box. That's with replacement. So the next draw, I still have 7 letters to choose from, but how many E's are there in charted? Again, only 1. So that's 1/7. And then that letter is put back in the box. Now, to draw D, there's only 1 letter in the word, there's only 1 D in that word charted out of 7 letters, so it'll be 1/7. So here I'm going to multiply 1/7. I'll just say the probabilities of the outcome, RED, we just multiply 1/7 times 1/7 times 1/7. That'd be 1/7 times 7 times 7 would be 343. So the probability of the outcome RED in that order, if 3 letters are drawn with replacement, it would be 1/343. Now, part B is without replacement. That means that once we draw a letter out of the box, that letter that we draw out of the box will not be put back in for the next selection. So, to select an R on the first draw, that probability will be 1/7. But this time, let's say that letter is not replaced. So now, instead of 7 letters to be selected, we now have 6 letters to be selected. For us to select an E, there's only one letter, there's only one E in the word. So it'll be 1 out of 6. Now let's say that letter is not put back in the box. We want to select a D. This time, instead of 6, we have 5 to choose from, but there's only one D. So that's 1 out of 5. So as you can see here, without replacement is that the sample size is being reduced by 1 on each on the successive draw. So the probability of selecting a red this time is going to be 1/7 times 1/6 times 1 over 5. This will be 1 over, and we're going to multiply 7 times 6 times 5. That would be 210. So the probability of the outcome, RED, in that order, if 3 letters are drawn without replacement, would be 1 over 210. Okay. Now, example 6 looks like this, and I'm skipping part D. Six blue socks, 6 white socks, and 2 gray socks are mixed in a drawer. You pull out 2 socks one at a time without looking. Complete parts A through, you're just going to do A, B, and C. In part A, you're going to draw a tree diagram along with possible outcomes and probabilities of each branch. And in part B, what is the probability of getting an event of getting 2 socks of the same color? Part C, what is the probability of the event of getting 2 gray socks? Okay, so let's start with the tree diagram, which is going to be part A. Okay, so in this case here, let's say we're pulling 2 socks one at a time. And this is going to be done without replacement. Okay, so on the first draw, it's either going to be a blue sock, which I'll label as B, or a white sock, which is W, or a gray sock, that'd be G. Let's add up how many socks there are in the drawer. There's 6 plus 6, that's 12 plus 2, there are 14 socks altogether. So the probability of pulling out a blue sock would be 6 out of 14. Or if I reduce that, it'll be 3/7. And the probability of pulling out a white sock on the first draw, that's also 6 out of 14, which is again 3/7. And then pulling out a gray sock, there are 2 gray socks, is 2 out of 14. That reduces to 1/7. Okay, you can see the sum of these individual probabilities along the branches add up to 1. Now let's go to the second draw. This is without replacement, so you're either going to pull out a blue or a white or a gray. And the number of socks will be dropped from 14 to 13 this time. So if a blue sock was drawn and there were 6, you're going to be down to 5 out of 13. So that means the probability of drawing a blue sock, given that a first blue sock was drawn, that'd be 5 out of 13. But for a white sock, if a blue sock was drawn, you're still going to have 6 socks, but it's now going to be out of 13. And then for a gray sock, you'll still have 2 gray socks if a blue sock was drawn. So it's 2 out of 13. Now let's say if a white sock was drawn. You can still select a blue or a white or gray. So if a white sock was drawn, you still have 6 blue socks, but this time it's going to be out of 13 because now you have 13 socks left. Now, if a white sock was drawn, instead of 6, you're going to have 5 white socks out of 13. And you'll still have 2 gray socks out of 13 if a white sock was drawn on the first. And now, for let's say on the first draw, it was a gray sock. So it's either a blue or white or a gray. Okay, you still have 13 socks left to choose from, but you'll have 6 blue socks to choose from out of 13. If a gray sock was drawn, you'll still have 6 white socks to choose from out of 13. And this time, if a gray sock was drawn, you'll have 1 left over out of 13. 1 gray sock left over out of 13. All right, so that's the tree diagram. Now, let's do the outcomes of each one and probability for each one. So a black and a black is one outcome. A black and a white is another outcome. A black and a gray is the third outcome. A white and a blue. Well, I'm saying black, that's blue. White and a blue, white and a white, white and a gray. And then gray and blue, gray and white, gray and gray. Now we're going to multiply along the branches for each outcome. For a black and a black, that's 3/7 times 5 over 13. This will be 15 over 91. But for a black and a blue and a white, blue and blue is 15 over 91. Blue and a white, that would be 3/7 times 6 over 13. That would be 18 over 91. And then a blue and a gray, 3/7 times 2/13, which is 6 over 91. And now a white and a blue, that would be 3/7 times 6/13. That would still give me 18 over 91. Then a white and a white, 3/7 times 5 over 13. This will be 15 over 91. And then a white and a gray, 3/7 times 2/13. This will be 6 over 91. And then for a gray and a blue, 1/7 times 6 over 13. This will be 6 over 91. For a gray and a white, 1/7 times 6 over 13. That's still going to be 6 over 91. And then 1/7 times 1/13, 1/7 times 1 over 13, 1 over 91. And if you add those individual probabilities for each outcome, you should end up getting 91. And which I do right here. So the sum of these probabilities for each individual outcomes have to equal 1. All right, so now let's answer we got part A. Let's answer part B. What's the probability of the event of giving 2 socks of the same color? Well, this time, a blue and a blue, a white and a white, a gray and a gray. We need to add those probabilities together. All right, so let me pull this down. The probability of a blue and a blue plus the probability of a white and a white plus the probability of a gray and a gray. So we just add those individual probabilities here. For a blue and a blue, that probability was 15 over 91. For a white and a white, that probability was also 15 over 91. For gray to gray, that probability was 1 over 91. Let's see, 15 plus 15 is 30 plus 1 is 31 over 91. That would be the probability of getting 2 socks of the same color. All right, now part C is this. What is the probability of getting 2 gray socks? The probability of a gray and a gray, well, that's given to us right here. Here are 2 gray socks. The probability of that would be 1 over 91. 1 over 91. Okay, let's talk about conditional probabilities here. When the sample space of an experiment is affected by additional information, the new sample space often is reduced in size. Let's say that we toss a fair coin 3 times and consider the following events. Event A is this, getting a tail on the first toss, and event B is getting a tail on all 3 tosses. And I'm going to let S be the sample space in the figure below. We see that the probability of event A, that's going to be this circle that I'm outlining here. The whole sample space is this. That's all the possible outcomes of tossing a fair coin 3 times. And in event A is getting a tail on the first toss. These are the possible outcomes of getting a tail on the first toss. There are 4 possible ways of doing that out of a total of 8. So the probability of event A getting a tail on the first toss would be 4/8 or 1/2. The probability of event B is the probability of getting a tail on all 3 tosses. There's only one way to do that, and that's this. That's 1 out of the entire sample space, 8. 1 over 8. Now, if event A has occurred, then the sample size is reduced to event A. The probability of the events that all 3 tosses are tails, given that the first toss is a tail, will end up being 1/4. So here, this right here represents getting a tail on the first toss. Given that this has already happened, a probability of getting all 3 tails on all 3 tosses is 1 out of 4. Okay, so for this situation here, we use this notation. And we read that as the probability of event B given A. And this is how we write the probability of event B given A has already occurred, equals, in this case, 1/4. All right, so this is the definition of the conditional probability. Now, more than likely, you're not going to be using this formula directly, because usually conditional probabilities can be done intuitively rather than using this formula, but I'll give it to you anyway. If A and B are events in the sample space S and the probability of event A is not equal to 0, then the conditional probability that an event B occurs, given that event A has occurred, is given by this. The probability of B given A is this. The probability of the intersection of A and B divided by the probability of event A. Okay. Now, we're going to use what I talked about with you intuitively with this example. Okay. Now, let's pay close attention to what's given to us. There are 40 employees in a certain firm. We know that 30 of these employees are male, six of these males are secretaries, and 11 secretaries are employed with the firm. What is the probability that an employee chosen at random is a secretary, given that the person is a female? And I'm going to underline this because they're giving you information regarding males. We want to find out the probability that an employee chosen at random is a secretary, given that the person is a female. So we have, let's take what we have here. 40 employees at a certain firm, 30 of them are male. All right, so let's find out how many females we have. We got 40 employees. So if 30 of them are male, subtract 30 from 40. That would give us 10. So we know 10 of these employees are female. I also know something else. 6 of the males are secretaries, and 11 are employed by the firm. Let's find out how many female secretaries we have. Okay, 6 of them are male, but 11 secretaries are employed by the firm. Subtract 6 from 11, you're going to get 5. So from this, we can find out what the probability is of randomly selecting an employee that is a secretary, given that this individual is a female. Well, we know 10 of them are female. That would be my denominator right there. And out of those 10 females, how many are secretaries? 5. So the probability of randomly selecting a secretary, given that the person is a female, would be 5 out of 10. We can reduce that to 1/2. See how easy that was to get the use the conditional probability without using that formula that I showed you. So here we can do this intuitively. Okay, so that does conclude this video in section 9.2 dealing with multi-stage experiments.